So just a quick recap. Having thought about the idea of equilibrium being the point at which a forward and a back reaction are going at the same rate, so it doesn't seem that anything's happening, we've got this idea of the equilibrium constant, but we've got issues on the values we can use in calculating it, depending on what phase or state, if you like, the reactants and products are in. So we looked at the homogeneous one is the easiest one, where everything's present in the same phase. So they could be all gases, for example, or all in solution. And if we used equations to represent the reaction, what you've got to bear in mind is the molar quantities in there, and it's ratios, you know, all the way through. It's about ratios, and it doesn't matter whether it's 2 to 1 to 2 or 4 to 2 to 4 or 100 to 50 to 100. That ratio is just the same. And of course we were getting onto fractional molar quantity, so you could have 0.2 to 0.1 to 0.2, and those are the reacting quantities. And ultimately, of course, we were trying to separate out this idea of the starting quantity, which was just an amount you were mixing together, the amount that reacted, which was what the equation represented, and the equilibrium quantities. Now, it's you know, the piece of information that's really key to it all is usually something on the right hand side telling us how much of a product we've got. And we came down here to the that forward reaction where A and B are reacting to give you C and D. The equilibrium constant is calculated like that, and I don't think we had any big problems with that. The small letters used as indices on there are the molar quantities in the equation. So we had as an example the contact process one, where sulfur trioxide was the product from sulfur dioxide and oxygen. And we did the same playing with units, didn't we, as we'd done with the rates, and the only thing that was missing from this was per second. That was the only difference that we had there. Otherwise, we were doing the same thing. This idea of cancelling sometimes really throws people, and yet it's actually quite sort of basic maths, really. It's maths I did in primary school, but I don't know if they do it now. You know, cancelling things out on both sides or top and bottom of a fraction, getting fractions down to their smallest forms, and that fractions seem to scare people. You know, where you've got something over something. But they're, you know, easily manipulated when you know how. We also considered the Haber process for making ammonia, and then a quick skim through an example of a heterogeneous equilibrium where you've got substances present in more than one phase. And we actually decided that you'd done one recently, of course, and produced solid sulfur, gaseous sulfur dioxide and liquid water by mixing together two solutions, and that was the thiosulfate and acid one for the rates. So that was quite a handy one. And then I appear to have left a blank page. That's really useful. Now, this was where it sort of started to get complicated. And at first, you know, when you looked at this, very few people had an idea how to start, but hopefully it got clearer, didn't it, as we went through. The important thing, okay, now that's number 2, so number 1 should have been on this page, shouldn't it? No, okay, it's right down there, obviously. Yeah, I don't know why I hid it down there. The important thing is to start with your equation and look at the reacting quantities, the reacting ratios, if you like. 2 moles on this side, 1 mole of that, 1 mole of that. And then when you're told something about the equilibrium mixture containing a certain amount of a product, you can then work out all the molar quantities in that equation. The problem that we had was that the starting quantities can cause well, they can be a distraction, can't they? So that this 0.218 mole sample of hydrogen iodide, you know, is not what reacts. That's what you're given, and some of it reacts, and disappears. It's no longer there. It's turned into hydrogen and iodine. What's left is the equilibrium concentration. So the equilibrium concentration of a reactant is the starting quantity minus the reacting quantity. All right. And so we worked some of these out, and actually it did seem to get easier, as we went along. And there was also this idea that when you're given something if you're given gases in a flask, you will sometimes be given the volume, and sometimes it will just be given as V. Usually it's given as V when you've got the same number of molecules or moles on each side. So with this one, we've got 2 Hi on that side, so we've got 2 moles or molecules of gas on that side. And similarly, we've got 1 plus 1, we've got 2 on the other side. If it was uneven, then we would need to consider the sort of concentration of the gases. That where you've got the same number on each side, then if you were to do the equilibrium constant calculation using actual concentrations, so that much per unit volume, that much per unit volume, that much per unit volume squared, they actually cancel out again. And again, it's that idea of cancelling out that's quite important. And it's because you've got the same number of moles as same moles of products as you had reactants. And the calculations seemed to come out all right once people had beaten their calculators into submission. Similarly, working through this one, and you didn't have to worry about what the compounds were. You can refer to them as A and B and C and D if you want to. What the reaction is not particularly relevant in these calculations. So this was an organic reaction, an acid and an alcohol giving us an ester here and water. That's the equivalent of acid plus base gives salt plus water, and ester is just an organic salt. And it was the same sort of calculation, the same sort of reasoning at the end as well, so I don't think we'd got any huge problems by the time we got to that point so far. The next bit I rushed at the end and gave you some information on, by the time I'd worked out the right version of it and reprinted it, Le Chatelier's principle and the equilibrium constant. And the important thing here really is to remember that only temperature has an effect, right? The others don't. So just to make the point, changing concentrations, no effect. Pressure, no effect. Catalyst, no effect. Right? It will change position of equilibrium, but not the equilibrium constant. Temperature, on the other hand, does make a difference. And that, of course, is then where you have to start considering whether it's an endothermic or exothermic reaction, and using my sort of idea of taking heat as a reactant or a product. It's a reactant in an endothermic reaction, it's a product in an exothermic reaction. That's not a sort of standard way of thinking about it, but I think it helps you understand what the effect will be. If you increase the temperature, you're increasing the heat on whichever side, it's going to push it to reduce the temperature back down. So that's the only one that is really going to have any effect. So I'm going to give you these practice A-level questions, which is partly about the equilibrium constant, partly about Le Chatelier's principle as well. And what I would suggest is that you work together on these, because these will be the biggest help in doing the assignment ones. Now, I'm doubtful whether we're going to perhaps get onto those properly today, but we'll see. Yeah, by the time I've actually given you enough time to go through these, and then we've worked through the answers, then you're going to have to try and remember it for next week, which is not ideal, but we'll see what happens. We'll see. Okay, if we have a look at question 1, I've not managed to snip the question numbers in with this by the looks of it, but hopefully this hasn't caused too much trouble. The beginning bit of this, the equation is just making nitrogen monoxide out of nitrogen and oxygen. That's not terrifically difficult, I hope, to write an equation for that. What are we going to have? N2. We probably ought to say it's gas, oughtn't we? and oxygen. And what we're going to get on the other side? 2 NOs, yeah. I haven't really left enough space for putting the Kc expression in there, but the problem is I just literally copied these off A-level. It was a booklet of questions that, you know, some A-level teacher had put together for his class, and yeah, so sometimes there isn't enough space and sometimes there's too much. So what are you going to have on the top? NO. Yep. And then on the bottom you've got the other two, yeah. Okay, so that's fairly straightforward. Products to the power of 2, reactants to the power of 1. This graph then, as the temperature goes up, you've got Kc is getting bigger. In other words, if you've got this, what was it, A to the A, this general expression. Oh, no, it wasn't that, was it? Yeah, it's C and D on the top. It's easily done. C and D over the A and B. Then if Kc is getting bigger, it means that the top of that expression has got to be getting bigger. You know, think about it. 3/8 is more than 2/8, which is more than 1/8. You know, if you increase the top, it gets bigger. So given that C and D are the products, it means that as we're increasing the temperature, we're getting more products. So we're putting more heat in on the left-hand side. That's pushing the equilibrium towards the right-hand side. So this tells us it's endothermic. So you've got more products, or more, yeah, with increasing temperature. Okay, then you have, yeah, something to think about. If the value of Kc for this reaction ends 1 times 10 to the minus 5, it's not very much, is it? At 1500 K, we're not given any particular values on there. Explain the significance of this value for an industrial chemist interested in manufacturing nitrogen monoxide by the direct combination of the elements. What's the product yield like? Pretty small, isn't it? So the yield doesn't actually justify the cost of producing that high temperature. Yeah, it's, you know, you've got to sort of think about, you know, there are very often different ways of producing chemicals, and in industrial applications they have to make the choice, and it's going to depend on cost. And the cost of energy, of course, is a big deal in a lot of chemical reactions. It's one of the reasons for using a catalyst, because it means that you can, if there is a catalyst available, you can run a reaction at a lower temperature, that sort of thing. And with this one, 1500 K, I mean, that's, you know, that's seriously high temperature, isn't it? And we're still only getting a Kc of 1 times 10 to the minus 5. In other words, you know, it could be 1 times 10 to the minus 5 over 1. Well, we're hardly getting anything for, you know, huge temperature. So the significance of this is really that the yield is very small. And it doesn't justify cost of high temperature. So they'd find another way of doing it. They wouldn't react together the nitrogen on oxygen, or they'd use a reaction that had a catalyst. I don't know if that one does. Well, if you think of some of the others that we've had some that were, trying to think what we had yesterday. Let's have a look at some of those examples. We had If we had 0.26, you know, you're talking about 2 times 10 to the minus 1. You know, it's hugely bigger, isn't it? You know, in terms. So that wasn't a very scientific description. And no, the other one, which of course is. Sorry. Oh yes, yeah. 0.172 there. 0.0179, 55.9. So, you know, it's a relative thing. And I mean, if it's a very valuable reaction, then it, you know, it might be worth doing it. But, you know, to have a value of, got to come back to it now, haven't I? Yeah, 1 times 10 to the minus 5, we're talking, right, that's to the minus 1, 2, 3, 4, you know, we're talking that, aren't you? Really, yeah, pretty small. You wouldn't want it to, perhaps less than a sort of couple of decimal places in. Right, part D on this one over the page is part of the same question, isn't it? When cooled, nitrogen monoxide reacts with oxygen to form gaseous nitrogen dioxide. Okay, this is a different scenario. Nitrogen monoxide then, have we got an equation for this? We need 2NO. Yeah. And we can have an O2 gas. That's going to give us, yep, 2NO2 gas. All right. So, the questions that go with this then. State how an increase in pressure would change the position of the equilibrium and the value of the equilibrium constant for this reaction. So what about the position? It moves to the right. Yeah, because if you increase the pressure, you want to try and reduce it. Le Chatelier's principle says that it will try and reduce the disturbance. Okay, you've got an equilibrium. If you put it under pressure, the equilibrium will move to try and reduce that. And the easiest way to reduce it with a gas is to have fewer particles. And you've got fewer particles on the right. You've only got 2, whereas you've got 3 on the left. So it moves towards the right. That reduces the number of gas molecules there are, so it will reduce the pressure. So the change in the equilibrium, you've only got a state on here. You haven't got to explain it. So it moves to the right. And what effect does it have on Kc? Yeah, yeah, no effect. Right. Are these looking sort of doable? Yeah, they might be by the time we've done all 3 of them. All right, this looks familiar. You tend to get, this is one of the things about chemistry, you get the same examples used over and over again. So question 2 then, the reaction between hydrogen and iodine, yay. Represented by the following equation. So we've got hydrogen gas and iodine gas in equilibrium with hydrogen iodide, because we've had that the other way round as well. Worth noting that you've got, that should be a delta H if you've got a little box with a question mark in it there. That's, I have no idea why. Some of them I think came out right, but mine's got a odd version of that. So that's delta H is plus 52 kilojoules per mole. So what sort of reaction is that? Endothermic. Positive. You're putting heat into it. The chemicals gain heat. All right. Really, yeah, it's one of those things that no matter how many times we do it, yeah. Okay, so write a Kc expression for the decomposition of hydrogen iodide. Ooh, that's the other way around, isn't it? Okay. At a given temperature, the value of Kc for this reaction is 20. What would be the value for the is that a, no, that is all one question, isn't it? Right, what's the expression going to be? Kc equals, yeah, the H2 and the I2 have got to be on the top, haven't they? Because it's actually the back reaction that we're being told to do. So we've got the H2, we've got the I2, and then we've got on the bottom HI to the power 2. So that's the first bit. At a given temperature, the value of Kc for this reaction is 20. What will be the value of Kc for the reaction between hydrogen and iodine at this temperature? So, well, we did it yesterday. It's 1 over because it's the other way up. Yeah? All right. So if it's 20, it's like that. That's what we're being told, isn't it? That the value of Kc for this reaction is 20, which is 20 over 1. So Kc for the back reaction is the other way up because this would be on the top and this would be on the bottom. So it's 1 over 20, which is there for a while. All right. Okay, part B of this one. The pressure of an equilibrium mixture of hydrogen iodide, hydrogen and iodine was increased. We shouldn't have too many problems with this. State what, if anything, would happen to. Interesting. Oh, well, there's 2 marks for the, yeah. It's a bit obvious, actually. What would happen to the rates of both forward and reverse reactions? If you increase the pressure, rates of react, what happens to the rate? It'll increase, yeah. And will just one of them increase or both? Both, yeah. If you think about it, it's like increasing the concentration, isn't it? The particles are closer to each other, more collisions. So the rates, this is going back to the last chunk. So the rates of both will increase. Position of equilibrium. It will stay the same. Yeah, because you've got equal numbers of molecules on each side. You know, it can't reduce the pressure. It can't go in either direction to reduce the pressure, can it? Much as it would like to. It can't but you know, much as the drive, according to Le Chatelier, if you increase the pressure, it will attempt to reduce the pressure by making fewer molecules. Well, you can't push that one either way to get fewer molecules, so it won't have any effect. So that is not always going to be the case, remember. You know, if you've got different numbers of molecules on the 2 sides, then increasing the pressure will favour the reaction that produces fewer molecules. Does that make sense? And the value of the equilibrium constant then, and that's going to be no effect. Okay. Hopefully, you know, you'll have enough examples and also be able to fish things out of the notes, I think, to be able to do this. All right, and is this the last one, third one? Yeah. Oh, goodness me. Right, I'm going to need more space than that. And I have to move this down. There's a lot of working out to go with this one. I don't suppose anybody's got as far as this, have they? Okay. This is one of the actual calculations that we were doing yesterday. All right, the others have been a bit tame so far, haven't they, really? None of that working out the, you know, number of reacting moles and that sort of thing. Okay. Now, this, well, let's let's work through the information first. A flask containing a mixture of 0.2 moles of ethanoic acid and 0.110 moles of ethanol was maintained at 25 degrees C until the following equilibrium had been established. All right, so those were our starting values, though those are not the reacting values, those are not the equilibrium values. The ethanoic acid present at equilibrium required 72.5 centimetre cubed of a 1.5 moles per decimetre cubed solution of sodium hydroxide for complete reaction. That's a bit like when you did that indigestion tablet and you had to titrate what was left to find out what had been used. Do you remember? You reacted acid with the indigestion tablet and then you titrated the excess acid with sodium hydroxide to find out how much acid had reacted to work out how much carbonate there was in the tablet. That's a long time ago, isn't it? So we've got to calculate the value of the equilibrium constant for this reaction at 25 degrees C. Well, we've not got any information like we've been given before, but we're in with a chance of working out the ethanoic acid bit. So we're going to have to do a bit of backwards working on this. And this is far more complicated than the ones that you get on the assignment sheet. All right, but it's just to make sure that you're competent using your moles and things. All right, we've been told how much sodium hydroxide was used, so that's probably a good starting point, isn't it? If we do moles of sodium hydroxide, we'll be able to work out how many moles of acid were left at equilibrium. Then we'll be able to work out how much reacted. So if we do that, so moles of sodium hydroxide, well, what are the moles of sodium hydroxide? What were we told? We've got this information here. It would be 1.5 if we had a whole decimeter cubed, but we haven't, have we? What have we got? 72.5, yeah, which in terms of a fraction of a decimeter cubed, it's 72.5 thousandths of a decimeter cubed, isn't it? Yeah? So if you work that out, you'll work out how much sodium hydroxide was needed. Let's see if we can get a number from anybody for that one. It does depend how you round your figures on this as to how this works. I would go to 3 decimal places, I think. So, yeah, 0.108, yeah. Right, okay, we have a starting point then. Now, if that was the amount of sodium hydroxide that was needed to neutralize the acid left at equilibrium, how much acid was there at equilibrium in terms of moles? Same, yeah. Yeah, all right. So the moles of ethanoic acid, and I don't know whether you really probably need to write the equation in there, but the moles of ethanoic acid at equilibrium, I'm just going to write equa, is also that then, because if we needed that many moles, it's a 1-to-1 ratio, and we'd really need the equation for sodium hydroxide plus ethanoic acid somewhere. I'll write it in at the top. Sodium hydroxide plus CH3 COOH gives us CH3 COO, and then we get the Na stuck on the end, which is weird, but that's the way it works, and water. So that is that reaction. That's what that's doing. All right, so it's analysing what's left by titrating it with something else. Okay. Now we have then acid plus alcohol gives ester plus water. That's, you know, it's the sort of thing we had with the example yesterday. The amount of ester that we've got is the same as the amount of water, isn't it? And that's going to be the same as the amount of acid that reacted. How much acid reacted? No. How much did we start with? Yeah. And how much reacted? Oh, sorry, how much is left? That. So it's that minus that. This is a different, it's another calculation. We've been working out the other bits. 0.0. Yeah. Yeah. Yes. Makes more sense. Right, so if we look at the moles of ester, right, rather than writing out CH3COO, C2H5, and we're just going to put ester equals the moles of water, which also equals moles of acid that reacted. Now, you know, we've been having to work that out before, so this is not new. And that then is the 0.2 that we had up on the top bit of the information up here. 0.0. Oh, no, it's not. 0.2. I've got the zeros mixed up, because 0.200 minus what's left. We don't need this for the acid bit, do we? Because we know that at equilibrium we've got that much acid, but in order to find out how much of everything else we've got, we need to know how much acid reacted. So we've got that, which is, where were we? 0.92. Yeah, lose the decimal places after a while. Okay, so we've got the moles of acid, the moles of ester, the moles of water. The one thing we're missing is the moles of alcohol, isn't it? So have a think. Nope. What have I got? I'm starting here with 0.109 and I have no idea why. It should be, yeah, it should be what we started with, shouldn't it? Minus what reacted. How odd. Yeah, I don't know. My working out on here, I must have got from a sort of answer sheet that went with this. Not entirely sure, unless that is, yeah. Well, we started with that, yeah? The moles of acid that reacted has then got to be the same as the moles of sodium hydroxide that reacted, yeah? So if we say, oh, yeah. That sounds about right. 0.018. And I'm running out of space. And then all you've got to do, this doesn't want to, Then we've got to work out our Kc. Now I'm not going to put all the formulae in. On the top we've got our products, our ester and our water. Write them in. We haven't got any indices because there are no molar quantities other than 1. And then we've got our acid and our ethanol. I could have put alcohol, couldn't I, on the bottom. All right, so we've now got to work out our concentrations here. The ester and the water are these ones. You could just put 0.092 squared, but you know, to put it each bit in explains it. All right. So those we've been given one of those usually before, one of the products, but not this time. We've worked them out. How much acid is there left at equilibrium? I believe we worked that out somewhere. Yes, that's up there, isn't it? Okay. 0.108. And the alcohol, we appear to have just done that. It's that one, yeah? The numbers are too similar. 1s and 0s and 8s. Getting to mess with that. It comes out somewhere between 3.7 and 4.9, depending on the values that you use in this, and I'm not sure. Give me that again. 4 point. Let's call it, round it up to 4.4. Yeah. Well, if it's, yeah, it depends where you've rounded, really. Yeah. Yeah. Yeah, it doesn't. On an A level answer mark scheme, the values they've got, and I've done a bit of a mix and match on my copy here, where I've taken average values, which is not terribly helpful. But the outcome for this is anywhere between 3.7 and 4.9. Yeah, yeah, depending on how you round that. So, well done. All right, we're getting there. Hang on in there. The enthalpy change for this reaction is quite small. It's not really relevant to what we're doing, but by reference to the number and types of bonds broken and made, explain how this might have been predicted. I'm not really expecting that in here, but it's just that you've got similar types on each side. You've got very similar bonds being broken on the left and formed on the right, so there's not that much difference between them. So the actual enthalpy change is quite small, but that's not a bit that you would need. It's really a bit of understanding the energy side of it, I suppose. And it could be the same number of bonds, actually. Right. Okay. Now, you've got a fair bit of reference material then. Do you want to have a go at the assignment and get it out of the way? I'm not sure, but it's about the same size as that. Right, okay. If you don't finish it, you could leave it in the box and then, can do it. It can be done next Thursday morning. Yeah, I don't think I've got anything else booked into that session. It's up to you. For some people, having just done that and just got it in your head, you might now be ready to give it a go. You will need to look in your notes, and you'll need to look at some of the handouts, because there's little bits of information that are asked for that I haven't gone over. There's, for example, I ask about an example of a catalyst. Now, one of your handouts from when we started this just before Easter has actually got a table of catalysts on it, and it talks about the effect of catalysts. So you will need to hunt around a little bit, But it's up to you, really. I think the let's have a look. See how big it is. No, it is bigger actually. Well, you leave it. You leave it, yeah, because that's going to then give me the, an idea of grading, isn't it? There are two, four, five sides in this. And it asks a little bit more explanation about the effect of the changing conditions, applying Le Chatelier really. But yeah, well, I'm going to let you decide actually. If you feel that you've sort of got the hang of that enough to give this a go straight off, and might think that if you leave it for a week, you'll forget everything, then that's fine. You can do it now. Or if you just can't stand any more of this at the moment, you want to go away and read everything and look at the practice ones again, you can leave it till next week. All right. How many for doing it now then? A few, yeah? Anybody want to not do it now? All right, okay. You can use all the notes, all the handouts, this sort of thing, and the stuff off Chem Guide as well. The idea is, that it's just that you're doing this one on your own. You've been working together, comparing notes with each other, and there are enough questions on here that you don't have to answer everything to pass. If you do some bits of it, I can judge. You've got these two assessment criteria here, 2.4 and 2.5, which off the top of my head I can't remember what they are, but I can pick pieces out of what you do on here. You don't have to answer everything. If you're going for higher grades, of course, then you need to be answering more and putting more explanation in. All right, but rather than having to go away and research it and look elsewhere for material, you should have enough in your notes. All right, all giving it a go then, yeah? Okay. If you do get to a point where your brain threatens to leave home, then you can just you can just put it in the box and come back to it either next week or I don't know, after a session or over a lunchtime.